Now we are going to discuss about magnetic potential energy in an inductor. Suppose we have an inductor here, right? So magnetic potential energy in an inductor. So what do you mean by inductor? Inductor is a component of electric circuit that possesses inductance. So you know inductance, we have already discussed about that. So represented by L, right? Self-inductance. Now here you see, suppose potential V is given here. This is the key or switch, you can say, and this is the flow of current in this direction. So due to this flow of current, when the current will increase from 0 to I, right? As soon as you switch it on, current will increase 0 to I due to this potential difference, and then this inductor, in this inductor an EMF will be induced, and that according to Lenz's law that will oppose the current. This induced EMF will oppose this current, right? That will be produced in the opposite direction. So as it opposes this current, that's why to maintain and to continue this current in this circuit, so it has to do it must do a external work. An external work must be done here, and that external work will be stored as electrical potential energy in this inductor, right? So external work that's going to be done here to continue this flow of current in this circuit will be stored as a magnetic potential energy in the inductor, right? So in the last lecture we have already discussed this. E is equal to minus L di by dt, right? L is self-inductance. So we have already discussed this in the last class, right? And here this V, potential difference V applied here, will be equal to this EMF. EMF is also nothing but potential difference, but its direction will be different. Okay, direction is opposite to this V. This V will be equal to minus E because of opposite direction. Now let us suppose dW, small amount of work is done in small time, in time dt, in dt time, right? Then we know power P is equal to rate of doing work. dW work is done in time dt, so therefore power is given by work done by time. Rate of doing work is power, so that's why this P implies, sorry, not P, dW implies dW, this implies dW is equal to P into dt, right? P into dt. Okay, now here you see, so what is P? Power. P is equal to VI. You have got this formula in class 10. P is equal to V into I. If you remember, you have studied in class 10 science, electricity, right? So you can use that formula. So we can write VI dt. Okay. Now here what we will do, we will replace this V by minus E, and we will replace only V should be replaced. Okay. Or you can do one more thing. Let us do one more thing. replace this E by this, right? So then what you will get? This is minus, that's gonna be plus, and then you will get L di by dt, right? So V can be directly replaced by this value, L di dt. So what we will have now, so now here from this, let's come here. So here dW will be equal to, dW is equal to inductance L di by dt, I dt, that's it. So here dt gone. So what we will have? We will have L I di. We can write that, right? Now, in order to find total work done, this current is increasing from 0 to I, right? As soon as you switch it on, then this current increase from 0 to, when it is switched off, when switch is off, then there is no current, 0. And as soon as you switch it on, then the current increases from 0 to I. So in order to obtain this, what will be the total work done? So total work done can be obtained by integrating dW, right? Integrating dW from 0 to I. So hope you have the idea of integration that you have studied in mathematics, differentiation and integration. So now dW is nothing but here L I dt. So as L is constant, it can be written outside, then 0 to I di. Now integration, you have got this formula that integration of x to the power n dx is what? X to the power n plus 1 by n plus 1, right? You have got this formula, x to the power n plus 1 divided by n plus 1. So here, instead of x, it is I here, so n power is 1 in this case. So 1 plus 1, 2, 1 plus 1, 2. That's why we can write here W is equal to L I square 1 plus 1, 2 by 1 plus 1, 2, I square by 2. Here we have limit 0 to I, 0 to I, right? So if you have limit here A to B, this is lower limit, this is upper limit, then what to do? You have to put the upper limit here, upper limit is B here, in this case B to the power n plus 1 by n plus 1. Then you have to subtract the result obtained by putting the lower limit, then A to the power n plus 1 by n plus 1. That's how we can do. So if it is 0, then this thing will be 0, right? Only we will get these things. So here lower limit is 0, so we will get W is equal to N I square by 2, or you can write half Li square. So this is the work done, and work done is nothing but it is equivalent to energy. So energy is stored in this inductor. The magnetic potential energy is stored in this conductor is given by U, which is equivalent to work done. That's why U is equal to half Li square. So this is the expression for magnetic potential energy stored in an inductor, right? So hope you have understood. Now let's discuss about mutual inductance. Let us discuss about mutual inductance. Suppose we have two coils here. This is suppose primary coil. The potential is given, right? Another coil. This is secondary coil. There is no potential in this coil, right? No potential is given in this coil. So when this switched on, current passed through this and a magnetic field will generate, right? This is suppose current I1. This is current I1. So I1 represents current in the primary coil. This is primary coil. This is secondary coil. Now this is the magnetic field generated in the primary coil, suppose B1, and some magnetic lines of force will pass through this, right? So let it be B2, magnetic field associated with this B2. As you switch it on, current increase from 0 to I1, and due to this current increase in current, there will be change in flux, and that's gonna be changing here also, and change in flux. That is suppose phi 2 in secondary coil. Let us consider change in flux, and here change in flux is here magnetic flux is suppose phi 1, and magnetic flux associated with the secondary coil is phi 2, and the EMF induced is suppose E2 here. Let us consider EMF induced is E2 in this case, in the secondary coil. Let us imagine that way. So what will happen here? Due to changing I1, there will be change in phi 2. So that's why this phi 2 is directly proportional to I1, right? So that's why we need a constant here to make it equal. Phi 2 is equal to this one, we will say M1, M. So M is nothing but mutual inductance. This is M, mutual inductance, and this process is mutual induction, right? The process of producing EMF, inducing EMF here, to oppose the change in the primary coil is mutual induction, and this constant M is coefficient of mutual inductance, or mutual inductance. You can simply you can say mutual inductance. So this is the form, right? Now here you see this M2, you can write M2 is mutual inductance of, so this M is mutual inductance of the two coils, right? You can say that way. Now here you can see, we know the induced EMF E2 in the secondary coil is nothing but rate of change of magnetic flux d phi by dt, right? Now you see, you may think that there is not only one term. So why I have written here d phi by dt, there should be n or whatever the number of coils there. You may think that way. So here you see, we have discussed this thing initially, that suppose we have one coil, then this EMF is given minus d phi by dt according to Faraday's second law, right? And if there are n number of turns, then there should be a n. There will be n if this phi is flux associated with only one turn of this coil, then only here we will write 1 n. If this phi is such that phi we know b dot a. Okay. So for one term it is b dot a. If there are n number of terms, then we write nba. And if you use this phi, this is the magnetic flux linked with the whole coil, then we don't need to put here n, because this phi is already nb dot a. Right? Clear, distinct? Hope it is clear. Now here you see E2 is equal to minus phi 2 is mi1. Let us put here. M is constant. M is a constant which is known as mutual inductance of the two coils. So that's why M we can write di1 by dt. Right? So this is the EMF induced in the secondary coil. So hope you have understood. Now let me tell you one more thing. And SI unit of this also Henry. Okay. SI unit of L and M, mutual inductance or self inductance, whatever. In both cases, SI unit is Henry. Remember that. Now this M depends on 4 factors. What are the 4 factors? This M depends on 4 factors. What are those? M depends on number 1. First one is number of turns in these two coils. Number of turns. In the two coils. Right? Then what is the next? Shape and size. Shape and size also does matter in this case. Shape and size of the coils, right? And also depends in the medium between the two coils and distance between the two coils, right? Medium between the two coils and distance between the two coils. So you have understood this. This is about mutual inductance, right? Now let us discuss about mutual inductance in two coaxial coils, two coaxial solenoids, suppose. So let me clean this. Mutual inductance of two coaxial coils. Mutual inductance of two coaxial coils. Right? Now, here you see, suppose we have two coaxial coils. One coil is this one. This is one coil. And another coil is, suppose, this. One is blue and one is red. Let us assume that. And they are insulated. They are made of insulating wire. Okay, don't worry about that. They are made of insulating wire. And this is suppose primary coil. This blue one is suppose primary coil. And the red one is suppose secondary coil. Secondary coil. Now, number of turns in the primary coil is suppose N1 and number of turns in the secondary coil is suppose N2, and current flows through this primary coil is suppose I1, and due to this current there will be magnetic field in this two coaxial solenoid. That is same for both. Suppose B, because they are coaxial, but number of turns is different. Okay, so same lines are going, same magnetic equal number of so these are imaginary, but though let us consider it way that same number of lines of field lines pass through both coaxial coils as they are coaxial. Let us consider that way. Now here you see flux associated with this primary coil be suppose phi 1, and flux in the secondary coil is suppose phi 2. Okay. Now here you see magnetic field B. We know magnetic field in a coil having n number of turns is given by, we have already discussed, if this core is there is no any material in the core, it is air suppose, in that case mu naught n1 I 1 by L. If the length of both the coil is suppose L, let us consider this length is L. So this one is the formula for n1 number of turns. There is n1 number of turns, and I1 is the current here, right? So this is the magnetic field. Now magnetic flux phi 2. And magnetic flux. So magnetic flux phi is B dot A, right? B dot A. If there are n number of turns, then NBA, n B dot A. So here n2 number of turns, so phi 2 will be n2 B dot A, B dot A. And in this case, the area vector, this area vector and the magnetic field are in same direction, so theta is equal to 0, therefore cos 0 is 1. So that's why we can write, simply n2 B A, okay, because cos 0 is 1, so we can keep n2 B cos N, right? So here you see B dot M is n B A cos theta. So here theta is 0 and cos 0 is 1, so that's why it's going to be nothing but NBA. So that's why we can write phi 2 is n2 BA. So hope it is clear. So now here you see this B can be replaced by this, right? Then what you will get? Phi 2 is equal to, if you replace this one by this, then you will get mu naught n1 n2 I1 by L, and here you will get A, right? You will get this. Now in the last exercise we have discussed that we have already got in the last not exercise, in the last class we have already got that phi 2, this is equal to M I1, we know this, and how it is explained in the last class, right? So from these two equations, this one and this one, what we will get? M I1 is equal to mu naught n1 n2 I1 by L A. So here I1 cancels, so what we will get? Mutual inductance of these two coils M is equal to mu naught n1 n2 A by L. This is the expression for mutual inductance of two coaxial coils, right? Now here you see one more thing, important thing. If we put a core of a material with magnetic permeability mu. Suppose we have put a core here of material whose magnetic permeability is mu. So for a core material of magnetic permeability mu, then this m is given by mu n1 n2 a by l. So this is the result. So hope you have understood this. Now remaining topics will be discussed in the next video. Okay.